In 2017, a mysterious object zipped through our solar system at incredible speeds. Dubbed Oumuamua, it is the first interstellar object we've ever detected. But by the time we realized it was in the neighborhood, it was already on its way out. With limited data, we aren't actually sure what it is or where it came from. Now, several research groups believe it is worth sending a mission after it. But with Oumuamua already over 6 billion kilometers away, is it even possible to catch up? And even if we could, would there be easier ways to satisfy our curiosity? You're watching Infinity Unveiled. Join me today as we explore the big questions Oumuamua left in its wake, what mission scientists are proposing to catch up with it, and how we're planning to be more prepared next time an interloper flies by. Oumuamua Basics. If you're new here, here are some Oumuamua basics you need to know. Oumuamua was first observed by the Pan-STARRS 1 telescope at Haleakala Observatory in Hawaii. The name actually means a messenger from afar arriving first, in Hawaiian. It's thought to be about 100 to 1,000 meters long and is most likely shaped like a disc or a cigar. What really elevated Oumuamua from an observational curiosity into a bona fide mystery, however, was what happened when it passed by the Sun. Oumuamua passed its closest point to the Sun on September 9, 2017, at a brain-melting 87 kilometers per second. But when it headed back into space, it didn't slow down like normal. Scientists watching it detected an inexplicable burst of acceleration counteracting the pull of the Sun's gravity. Rob Warwick, the researcher credited with the discovery, said its motion could not be explained using either a normal solar system asteroid or comet orbit. Comets are leftovers from the formation of planetary systems, which can be ejected from their home star's orbit by a gravitational kick. They also speed up when passing close to stars due to the volatiles in them melting and being released as gas and dust. So if we'd seen Oumuamua give off the same outgassing, there would have been no mystery. But as we touched on in another video, Oumuamua didn't show any characteristics of outgassing, no coma and no tail. Readings from the Spitzer Space Telescope also indicated it was at least 10 times shinier than a typical comet. Oumuamua's origins. A few weeks after its discovery, a fierce debate quickly erupted among scientists. Was this an asteroid, a comet, or something a little less natural, an artificial creation, proof of alien life? We don't know. But we do know it came from very, very far away. To find Oumuamua's home star system, astronomers traced its path back over millions of years. It seems to have come from the direction of the star Vega in the Lyra constellation. Scientists found 4 possible home stars Oumuamua could have come from, some as far as 81 light-years away, but there haven't been any definitive answers on its origin story yet. Now, it is over 6 billion kilometers away, moving at 26 kilometers per second toward Pegasus, about as far as Voyager 1 was when it snapped the famous pale blue dot image. Even if Oumuamua is not a piece of alien technology, it holds importance as the first confirmed interstellar object to enter our solar system. So, it is no surprise that scientists want to take a closer look at it. We noticed it only 40 days after it passed its closest point to the Sun, but by then, it was already 33 million kilometers from Earth. We sent ground and space-based telescopes into overdrive trying to answer the questions surrounding it before it escaped our grasp. But 2 months later, by mid-December, it was already too faint and fast-moving to be studied by even the largest ground-based telescopes. With limited data and more questions than answers, some researchers believe the only way to learn more about Oumuamua is to send a mission after it. Project Lyra. However, catching up to Oumuamua is a significant challenge for 3 main reasons. The first obstacle is gaining enough speed to catch up. Oumuamua is over 6 billion kilometers away and careening through open space at 26 kilometers per second. No chemical rocket that exists today can reach that speed, making a rendezvous difficult. Once we've caught up to Oumuamua, the second challenge is decelerating enough to actually study it. If we don't slow down, we'll shoot right past it and won't be able to collect any scientifically useful information. Thirdly, it is difficult to find such a small object in such a large galaxy. Remember, Oumuamua is just 1,000 meters long at most, tumbling through the vastness of interstellar space. Still, these barriers haven't stopped research groups from making plans to catch up. While accelerating to the speeds necessary to catch up with Oumuamua is difficult, it can be achieved through the use of gravity assists from other planets. The most famous example of a solution comes from Project Lyra, launched by the Initiative for Interstellar Studies. They presented two different trajectories we could send a probe on. The first requires three distinct changes in velocity. First, we accelerate the probe out of Earth's orbit and send it toward Jupiter. Once at Jupiter, the probe slows down enough to fall toward the Sun, since less energy is required to do that from Jupiter than from Earth. As our probe approaches the Sun, it travels at its fastest. At this point, the rocket engines ignite to give it the biggest acceleration possible for the amount of fuel carried, a technique called a solar obirth maneuver. By harnessing this technique, researchers predict their probe will shoot out of the solar system at over 70 kilometers per second. While that is definitely fast enough to catch up with Oumuamua, there are still a couple of problems. Such a close approach to the Sun requires a heat shield to protect the probe. The good news is that the tech for such a shield exists, as the Parker Solar Probe uses something similar. The bad news is that it weighs 72.5 kilograms, putting a limit on payload mass. Next, sending a probe from Earth to Jupiter, then to the Sun, and back out to Jupiter to be sent in the right direction is quite a long trajectory. There's actually a shorter way to do it. Preparing for the next interstellar visitor. But could there be a better way to get the data we want? What if we could have anticipated Oumuamua months in advance rather than after it had already passed by? Astrobiologist Karen Meach of the University of Hawaii, who led the characterization of Oumuamua after its discovery, says we'll soon be able to do this for other interstellar interlopers that might cross our paths. NASA estimates that an interstellar interloper similar to Oumuamua passes through the inner solar system once per year. Since they are so small, they are hard to spot, until now. The Vera C. Rubin telescope, set to become operational next year, would be able to spot these objects a whole 3 months before the telescope that detected Oumuamua. What's more, it will get busy building the Legacy Survey of Space and Time, a database of 2 million images taken over a decade. Conclusion. I told you no one knows what caused Oumuamua to accelerate past the Sun. But I didn't tell you that we know of 6 other objects that have shown similar non-gravitational acceleration. They are called dark comets, and 6 have been discovered so far.